Hello again. This is chapter 11 of Earth Science. We're going to talk about geologic time. So, geologists, we study, rocks and things like that, and these take millions of years to form. And geologists need different ways in order to tell one type of rock and, which one is older or younger. There are both relative ways of doing that, which we'll discuss, as well as, sort of scientific to get at an actual number with like radiometric dating. All right, so let's get right into it. So here's some historical notes as to how these different types of geologic explanations came about. So there was catastrophism. What that means is whenever you have a large, you know, catastrophe, whether it be a landslide or a tsunami or something like that, it's going to change the landscape. And this is what early geologists started to use as sort of time points in terms of, wow, okay, so this had to have happened after this or before that, depending on um looking at the various relationships in the rock record. And out of this, later, a bit later on, we they came up with what's called uniformitarianism. That's a long word, right? It's what that is the present is the key to the past. So geology, or how the geology of areas is formed, isn't any different today than it was several million years ago, or a billion years ago. The principles have stayed the same. So any rocks that are being formed now are formed in the same fashion than they were 70 million years ago. So that's a key principle in geology, to understand that you don't have to worry about some weird curveball being thrown at you in terms of how these rocks were formed. So the father of modern geology, his name was James Hutton, and he wrote some publications back in the 1700s. He was the one that really started this movement to try to figure out not just what kind of rocks they are, but how they were formed and what order they were formed, and the different environments in which they were formed in. So they started looking at placing rocks in events in sequence. And you'll see that obviously places like the Grand Canyon are the easiest to understand of that. And you'll see images of that through these slides, because it's a deep, deep canyon and it has lots of geology in it. So, and that's where these rules, these principles and rules come into play. So you have the law of superposition. All that states is, eh, all things being equal, the oldest rocks are always going to be on the bottom because they came first and everything else came after that on top of it. So the at the very top is the youngest rocks. Again, you'll see this in the Grand Canyon. It's the easiest pancake sort of layering to show this. So the oldest being on the bottom, the youngest being on top. But then you have this thing called principle of original horizontality. And what that is again, all things being equal, sediment is deposited flat. It's not deposited in any other weird shape, because if you know how things settle out, you know that it just sort of comes down evenly in layers, nice flat horizontal layers. And that makes sense. If you take, there's always that little geologic, we have them at UWM, where it's a jar of water filled with three different size grains. So you have sort of pebbles, then you have sand, and then you have sort of this muddy silt. And you shake it all up really good like that, and you just let it sit. Well, those pebbles are going to go to the bottom right away. Now this is more of a matter of weight, in terms of, they're heavier than everything else, but it's still the same rule apply, the same principle applies. The oldest ones are going to come to the bottom. In this case, they're the heaviest ones, and then the next one and the next one. So the first one, the oldest one, the first one to settle out is the heaviest ones. So that's the first one, then the sand, and then finally at the top, the smallest of all the particles that'll be uh, uh, settled out are sort of the clay silt minerals. And if you just looked at in terms of time, it might only take a few minutes for that to happen. But in those few minutes, the bottom ones are the oldest ones, because they they settled first, then the middle, and then the top. Then we have the principle of cross-cutting relationships, where if something kind of cuts across it, and you'll see images of this, it has to be younger than the material that it cut across because it can't cut across something that doesn't exist. So the original rock had to be there first, and you'll see images of this as well. So if you look at this rock image, it looks pretty crazy, right? But what you'll see is there's definite layering, and you could follow those layers through that, and maybe imagine that if you took this and you sort of stretched it out where it was flat again, you would see which ones are older and which ones are younger. So if you look at this image, these are going to be the oldest rocks down here. If I stretched them out in either direction, if I stretch them in that direction and that direction to flatten them out, these are going to be at the bottom. So these layers are older, and then a little younger, and then you get all the way up here, and these are the youngest. Okay, because like I said, think of like an accordion. So if I smush the accordion, everything on the bottom is still the oldest, and I bring it back out, it kind of reveals that. So that's what the rock layering is telling us, that we know from the law of superposition that these down here at the bottom are the oldest of these beds, these rocks in this particular set of layers, and then they get old, or excuse me, they get younger as you go up. There are rare instances where the oldest is not on the top, or where the oldest is on the top, but that's very rare, and that usually involves faulting of some sort. The law of superposition is well illustrated in the Grand Canyon. I've already mentioned this. So you have this sort of pancake layering of rocks, and just again, because of the law of superposition, the oldest ones are on the bottom and the youngest ones are on top. Okay. And because the Colorado River, water essentially eroded away what's now left of the canyon, we know that the water is always going to be at the top, the level surface. So at one point, the water flowed over the youngest one and started cutting into it and cutting into it, and eventually it gets down to older and older rock. Now, cross-cutting relationships, there's several different ways to illustrate this, but the one is a fault. So if you look at this particular image, you can see this really white layer right here and that same white layer up here. At one point, because we know the law of the principle of horizontality, we know that at one point those must have been like this, because everything, the sediments don't form like that. They form in horizontal layers. So that fault has to be younger than the rocks that it cuts through, because you couldn't have a fault cut through something that doesn't exist. So at one time they were like this, and now they're like this. They're offset. So that's the law of cross-cutting relationships. You have this in other things like igneous dikes and igneous sills, where you'll have much younger igneous rock cutting through much older rock because there was um, magma in the area at the time, or volcanism. The whole point of this chapter then is to start to figure out which rocks are older or younger than other rocks. And using the law of superposition and horizontality and cross-cutting relationships, along with the principle of lateral continuity, sedimentary beds originate as continuous layers that extend out in all directions. All right, so when you see sediment layers, you got to expect them, even though we always see it in sort of cross-section view, they actually go in all directions. All right. Now there are usually ends to them, and I'll show you that in a second. But when you're looking at relative dating like this, and you sort of, I don't want to say assume, because it actually is the case, that that particular sediment layer, except in very rare instances, extends out in all directions. They do come to an end eventually, but for the most part, when you're relative dating things, you can assume that it's going to go out in all directions. So let's take a look at this diagram here. So if we look at the middle of this diagram here, you can see it's all continuous all the way across. Same thing with this yellow layer and this limestone layer at the bottom. However, at some point, they do stop. So you see over here, they sort of butt up against what would be called the bedrock here, and they what we call pinch out. Okay, they pinch out into and they end, and that's to be expected because at some point, this rock here is much more less eroded. It's harder to erode, and it so you have sort of this basin effect here where all of these sedimentary rocks are sitting. You also get what are called pinch outs in the sense that they start to gradate into other types of rocks, and you can see that over here. That's actually very common because, like I said, the rocks themselves, the layers of rocks, at some point have to end. They don't go on for infinity, right? Obviously, the world isn't that big, so they have to end sometimes. And usually, what that means is that when this rock layer here, or these rock layers here, were deposited, at some point the environment changed. Maybe it went from a pure just trickling down through the water to more of a you know uh, a faster depositional environment, and there's whole science behind this, and I'm not going to go into all that. But what you need to understand is, it doesn't always stay the same. You can get changes laterally as well as with depth. Now, when you have, let's say, the Grand Canyon, right, and you have the Colorado River sitting down here at the bottom, if you see this type of rock over here and this type of rock over here, you can assume that at one time they were joined, right? You can assume that because you know that the principle of lateral continuity allows us to infer that, and that the water originated probably somewhere up here and just kept eating down in this direction, right? And now it's down into the super hard bedrock where it's kind of just, it'll keep eroding. It's just much more slowly. So same thing with this sort of brownish. Oops, that was a horrible line. Sorry. The brownish line here as well, right? So at one time this came across here, and the same thing with the yellow one. So that's the principle of lateral continuity. Now, the other things that we can use to help relative date are things like inclusions and what are called unconformities. And what inclusions are is when you have one rock contained inside of another rock. The rock containing the inclusions is younger. So, and I'll show you examples of these. And then you have what are called unconformities, which are breaks in the rock record. And that's usually caused by erosion taking place instead of deposition. So you have all of the rock being washed away and none of it coming back in. So if it's all being eroded away and then nothing comes back in, and then over, again, we're talking millions of years here, all of a sudden there is a new depositional environment where you do have, let's say, an inland sea comes in and covers that, you have new horizontal layers, you have these weird breaks in the rock that show you that at some point the environment changed, and I'll show you pictures of those as well. All right, so let's take a look at this. So let's look at inclusions first. Inclusions of igneous rock contained in the adjacent sedimentary rock indicate that the sediments were deposited on top of weathered igneous mass and thus are younger. So let's take a look at that. So you have this here, you have the sedimentary layer, right? This brownish looking layer. And then you have this igneous rock that's sitting in there like that. So the igneous rock had to have been there at some point first, right? Because it's it's a harder rock, but also um, it just the igneous rocks sort of, excuse me, the sedimentary rocks just sort of formed around these chunks of igneous rocks. So the igneous rocks had to have been there first. Then you have what are called xenoliths, and xenoliths are inclusions in an igneous intrusion. So you could see that this green stuff here came first. Okay, it's older than the igneous intrusion. The igneous intrusion welled up from down in the earth because it's heated, superheated, and what you have is it displaced all of this greenish looking rock around it, create and this probably went up here like this at some point and then got eroded off. Okay, all of that igneous rock came up, maybe like an old volcano, but along the sides of that, you have these little chunks here of the even older rock that are called xenoliths that were incorporated into the igneous intrusion. And these are actually fairly common. You do see these in highly igneous environments. Now, there are a couple of different types of unconformities. Now, again, an unconformity is a break in the rock record, and it tells a geologist that says, "Hey, something happened between the time these rocks were formed and the next ones above them were formed." Now, usually what that is some type of either erosion event or some type of faulting type of event. So if you have angular unconformity, you have tilted rocks overlain by flat rocks. And you'll see that, but let's say I have some flat rocks and then I got some stuff tilted right underneath it. That's an angular unconformity. A disconformity is strata that are on each side of each other, but they're still parallel. And again, I'll show you pictures of all of this. And then you have what's called a nonconformity, which is metamorphic or igneous rocks below, and you have the younger sedimentary rocks above. Okay, so let's take a look at how an angular unconformity would be formed. So we have deposition. Let's say we have a shallow sea here, and you have all of these horizontal beds, right? They're all flat for the most part. Then you have some type of uplift, let's say some type of igneous intrusion that or mountain building event where it starts to push things up. Once you have things pushed up like that, erosion goes faster. Okay, you'll notice this is water, there's no water here in the second image. So active erosion is taking place because of rain and things like that. And now that you have sort of this hill shape here, it goes much, much faster. So what you could see is that erosion has taken place and it's cut into all these beds. See how they sort of just stop like this right here? All right. And they stop. You could see they're all numbered. All the layers are numbered here. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the layering hasn't changed. What has changed is that the tops sort of, they went from rounded and the tops have sort of been shaved off due to erosion. So then what happens is over millions of years again, let's say a new ocean or a new shallow sea now covers that whole area again, and you go back to sort of step one, creating these layers on top. Now you have these flat layers sitting on top of these angled layers. And that's what I was trying to tell you. So the reason why this occurs, again, in a nutshell, is that over millions of years, the environment in which the rocks sit in changes. So in step one, we have a shallow sea, you get nice flat layering. Then it gets pushed up, either due to plate tectonics or something like that, and erosion starts to progress faster. Again, there's no shallow sea in step two anymore. So erosion is taking place actively from rainwater and things like that. Enough erosion takes place that maybe allows an inland sea to come back in. Okay, now you go back to that sort of flat layering again because you have this shallow sea that allows all that to percolate down in flat layers. So you get angled layers on top of, or excuse me, flat layers on top of angled layers. Again, like I mentioned, the Grand Canyon is the best example to show these types of unconformities. So let's take a look at these. So let's look at the angular one because that's the easiest to understand right away. So you have right here, you have these sort of this flat layer, then you have these angular layers coming into it like that. That's an angular unconformity. And I just mentioned that in the previous slide that the environment went from sort of tilted erosional back to sort of flat and depositional. You also have disconformities here and here where the rock layers are both um, uh, parallel, but they're very different geology. So at somewhere the environment had to have changed, and you still get this sort of weird break in the rock record where you go from one type of depositional environment to a very different one. And that could be plate tectonics again. It could be a lot of things. So, and then you have the non-conformity down here where you have all of this really old igneous rock down here sitting on below much younger, much younger depositional sedimentary rocks here. So that's a huge break in geologic time, going from that old igneous bedrock to um, much younger sedimentary rocks. Because these rocks here, these angled rocks, are older than these, and this is older than this. So if you look at it, the oldest would be this one, then two, if I can make it two, sorry, and then three. All right, so that basically this nonconformity here, let me erase this. This nonconformity here is separating not rocks one and two, but one and three. So you're almost skipping an entire section of geologic time because all of these rocks in section two here, these angular rocks, all right, all of those have been weathered away. So now you have one sitting on, or excuse me, three sitting on top of one, with one being the oldest. Now, correlation of rock layers is matching them up of similar age in different regions. So you'll see this as we go along, but this is sort of how they started figuring out like plate tectonics. So rather than just the rocks that are in the Grand Canyon, what about the rocks that are in the Grand Canyon and in another area in, let's say, Nevada or Utah or something like that? Do they match up in terms of their ages? And that's how you can start to figure out which one is older or younger. Again, this is relative dating. And one of the ways to do that is looking at what are called trace fossils, or fossil layers, where they have to pretty much match up. And if they do, then that particular layer is the same age, whether it's way over here or way over here. So what are fossils? Well, they're evidence of past life. These are some type of animal that's been, buried, and then there's a couple of different ways they do this. Either petrified within pores. They're formed by replacement, so everything of the original critter's been um, uh, replaced with some type of mineral. And then the way you actually find them is usually a mold or a cast or both. So a mold is sort of the filling. You could think of like a Jello mold, right? You fill this container full of Jello to get the shape you want. So that's a Jello mold. So the pan you're using is a mold. What you put in there is the cast. Okay, so technically Jello is the cast. Using my Jello mold example. There's also carbonization. So if you have critters or something that gets fossilized, the only thing that's left over is sort of a carbon residue. You have impressions, like footprints. You'll see fossilized dinosaur footprints and stuff like that. You can also have critters that are preserved in amber, spiders, flies, things like that. So here's some examples. You had petrified wood, which used to be wood, but it's been completely replaced by minerals. So now it's essentially like a rock. You have this trilobite. So this is the cast, and this is the mold, because it's the impression. You have this B here in section C, which the only thing that's left behind is the carbon residue. You have fish impressions, because fish don't have really hard parts that you can fossilize very well. So they leave sort of that impression in the sand. You have a spider encased in amber, which is like tree sap sort of. And then you have the real fun one, which is corporites, which is fossilized poop. And there are people that study this stuff. They're called corporites. And when they're found like that, oddly enough, they can use that to help determine how old the rock is. So there are different kinds of fossils and tracks. We mentioned that those are the impressions sometimes. Burrows, coprolites, like I just mentioned. Gastroliths, which are stomach stones. Um, and a lot of reptiles do this. They'll swallow a stone to help them grind food up as they eat. I don't know how you would tell that from any other stone, but okay. Now, the conditions that favor fossilization require that it be buried rapidly. And then they have to have hard parts. So if let's say we'll use a snail, right? If a snail gets is down in the sand and all of a sudden something whooshes over it really quickly and buries it fast, and then it just keeps getting buried, the snail got buried quickly, which will make it better for fossilization. But the snail also has a hard shell. That hard shell is what allows you to create the mold or cast, or in some cases, it'll actually be dissolved but then replaced by something else. So snail shells are pretty a good example of, because they crawl along on the bottom of something that could be buried quickly and then has that hard shell that could be left to fossilize. Now, there's the principle of fossil succession, which is they succeed one another and are definite in a definite and determinable order. Now, this is an old principle that started back in the 1700s and early 1800s. So, if you look at determining the age based upon fossils, you can see that there's certain fossils that are going to be older or younger depending on the type of fossil they are. So, for example, if I have a leaf here, okay, a leaf is basically just carbon, and in order to preserve that, it doesn't take nearly as much time or effort as it would, let's say, a trilobite. A trilobite's going to be much older, and this is how they start to determine these things. That we use the term trace fossil. There are certain fossils that of critters that are no longer exist on Earth anymore, and trilobite is one of them. There was a large extinction event right around the end of the Paleozoic that marked the end of the Paleozoic, in fact, 270 million years ago. Well, one of the things that didn't make it past that particular extinction event are trilobites. They no longer exist on Earth. They haven't existed since 270 million years ago. So if you find a rock that has a trilobite in it, you know it has to be Paleozoic age or older. And that's kind of how they look at some of this stuff. Now, not all fossils do that. So, for example, you could see this clam here, which we call bivalves, spans a long period of time. Okay, so the only way to make this particular chart work is to have these same observations from all different places around the world. And this was one of the first indications of putting sort of the theory of plate tectonics together, because they found fossils in Africa, and those same exact fossils with the same exact age in South America. So the fact that they had to have been formed at the same time under the same environment in the same kind of rock meant that at that period of time, those land masses had to have been together at some point. And that's how they started figuring out that the plates were moving around, and sort of the mechanics behind plate tectonics. And we'll get into that for that particular chapter. And I've already mentioned this. I got myself a little ahead of myself. We have these index fossils that are widespread and only exist for a short period of geologic time. And trilobite is one of the better ones of that. There's a few other ones as well. Dinosaurs, right? If you have a dinosaur bone, you know that the dinosaurs went extinct at the end of the Mesozoic, which was 65 million years ago. So if you have a dinosaur bone, that rock has to be somewhere between 270 and 65 million years ago, because that's when the dinosaurs ruled, was in the Mesozoic. They also went extinct. We don't have dinosaurs anymore. So we know that that rock has to be at least 65 million years old. So, and I mentioned again, what we're doing is correlating, trying to match up rocks and fossils of similar ages in different regions. And again, this is sort of the foundations of how they started figuring out continental drift and then eventually the theory of plate tectonics is looking at the fossils and how, hey, this had to have matched up at some point in time. So if we look at the correlation here, you can see, and I'm going to look over at my other screen here so I can see this. Here's three national parks. You got Grand Canyon, you got Zion National Park, and you got Bryce Canyon. Now they're all within a short short geographical distance from each other. I mean, they're within, so if you look at the rock record from beginning to end, all the way through that, you can see that there are some layers that correlate. So the very top of the Grand Canyon, okay, matches up with the bottom of Zion National Park, and the top of the Zion National Park matches up with the bottom of Bryce Canyon. And it goes from there. When you combine all three, you get a large from the this is geologic time from um, basically from today to the actual oldest rocks that the Precambrian rocks that are over 1 billion years old in some cases. All right, so the entire geologic time scale is represented between these three national parks. And somebody at some point said, "Hey, this matches up with this, and this matches up with this." So at some point, they all had to have been connected, but then sort of other geologic forces took place, maybe an inland sea or volcanoes or a lot of erosion obviously taking place to where you don't have all of this in the same rock record. But at some point in time, they all do match up. So this is relative correlation and relative dating. So we know that this rock down here has to be older than this rock here because this rock here is the same age and this rock is the same age. But this we know because of law of superposition, the one on the bottom has to be the oldest. So that makes this one up here the youngest. And that's how it's done. Now, the flip side of relative dating is what's called radiometric dating. Now, I chopped out some slides um, that kind of reviewed atomic, level stuff, atoms and protons, electrons. I kind of skipped over those. If you want to go review that, go back to, I think it was chapter 1 or 2 that talks about all of that. But I just figured for the sake of time, I would just skip those. So radiometric dating is using some known facts about certain elements and how they decay over time, and being able to take that and apply it to a rock that has even just small trace amounts of that element and determine an actual number, plus or minus, but still a number. This isn't just saying, hey, this rock is older than this one. This one's saying this rock is 2.5 million years old or whatever it is. So it all starts with what's called a half-life. So certain radioactive elements decay over time, and it takes them half this amount of time to decay half of their radioactivity. Now this gets more into physics and the physicists that determined all of this stuff. Um, but then once you have that half life, then from there, that half life goes another half life, that goes another half life. And they've been able to graph these out to figure out how long this takes. So when they're measuring these, they're trying to figure out where in that process that particular radioactive element is in its half life. But ultimately, it yields, oops, I am really bad at this. It ultimately yields actual numeric dates. But it's, not every rock can be radiometric dated. And it requires a lot of things like a closed system. You always got to make sure you check for accuracy. There's always a lot of source room for error in these measurements, but at least it gives you a good ballpark. Now, when you're dealing with rocks that span millions and millions and millions of years, it's not that big of a deal if you're off by a couple 100,000 years. What you're trying to do is get at least within the ballpark, within maybe a million years or so. Here's a radioactive decay curve, and I'm not going to go into this in gory detail, but what it's trying to show you is that one point you had 100% of the what we call parent atom, whatever that is, uranium 235 or 238 or something like that. And at that particular moment in time, you had zero daughter atoms. So what happens in radioactivity is as it loses its atoms because of spontaneous decay, it goes into other elements. So if you start with uranium, about halfway through, you'll see it goes down to 50 atoms here where they're exactly the same. All right. And then up here you have these are the byproducts up here, whatever what they call the daughter atoms. So as you get more daughter atoms, you're getting less of the original, let's say, uranium atom, all right, or rubidium or whatever they're using for the radioactive or carbon 14 dating, so that you get less and less of what was there originally. So when you take a piece of rock, and this is not easy to do, what you're looking at is the ratio between what's left over and what's still there. And that kind of gives you an idea of where that particular rock is in terms of its half-life. And once you have that, you can get a good idea of what the actual date is. Like I said, within 100,000 to a million years. Now, for example, carbon 14 dating is used primarily for much younger stuff. So it has a half-life of only 5,730 years. So it's used to date very recent things, especially those things that have carbon in them. Um, It's useful for anthropologists, archaeologists, historians, and geologists who study very recent Earth history. So this is what they use for like bones, like human bones, for of old, graveyard sites or something like that, old burial grounds of, really early humans. That's how they look at. This is how they're able to date things that they had to have had carbon or carbon dioxide at some point, and that's all absorbed by living matter. Again, this wouldn't work on those rocks in the Grand Canyon, for example. Those are way too old, but it does work for much younger rocks that have um, some type of carbon matter within them. Geologists use the geologic time scale to divide the geology into history of in units, and it was originally created using relative dates, although obviously some of the radiometric dating has helped sort of confirm where these particular layers should be. There are the main four subdivisions are what are called eons, and that's the greatest span of time in terms of uh, going back to when Earth first formed. So the youngest one is the Phanerozoic, which means visible life, and that's the most recent eon. That's when pretty much all life has taken place. Then you have the Proterozoic, which is sort of where life began. Its earliest forms. Um, in terms of maybe some bacteria or something like that. Then you have the Archean and the Hadean. Now, those are obviously the oldest ones. This is when, that especially the Hadean, named after Hades, is when, the Earth was first forming and condensing, and Hadean kind of stands for hell, and that's probably pretty much what we would expect to see during this time in Earth's history. There was no water yet. It was just a rotating ball of gas and volcanoes and things like that. And then you have subdivisions of each eon, which are called eras, and which is these are more of what geologists use in terms of looking at the rock record because it's an easier chunk of time to deal with, especially in our human brains. So the Phanerozoic has three eras, which are the ones that we really know about, that you hear most often. You have the Cenozoic, which is the most recent one, which we're in now. You have the Mesozoic, that's when the dinosaurs ruled the world, sort of the middle. And then you have the Paleozoic, which are, that's the ancient life when all the invertebrates ruled, things like trilobites and bivalves and gastropods and all that fun stuff. So those are the three main eras within the Phanerozoic, which we're in now. Now, eras are subdivided into periods, and then periods are subdivided into epochs. And eras are, much easier to understand. That we keep subdividing these because, even epochs are still long periods of time for humans to wrap their head around. Cenozoic or the Paleozoic is like 500 million years, or I forgot the exact number. So it's a long period of time for humans to wrap their heads around. So we keep breaking them down into smaller and smaller time units to better understand what takes place when on a scale that we can understand. Here we see the geologic time scale in sort of all of its glory. Now, there's a lot going on here in terms of, trying to cover all of Earth's history. Now, if you look at this geologic time scale from here to here covers most of Earth's history. In fact, it covers about 4 billion years. And in that 4 billion years, there's no life on Earth. Yet that's the bulk majority of the geologic time scale. So everything within the Phanerozoic, which is this section here, right? That's when life started to occur. So what they did is they broken this down, the Phanerozoic, and made it much, much more manageable by going through the three eras. You have the Cenozoic, again where we are now, the Mesozoic, which everybody knows because of the dinosaurs, and the Paleozoic. Okay, and then you have different periods. You have epochs, and then over here on the right it shows you the different ages. So there's a lot to look at here, and hopefully you recognize maybe a few things here. Here's Jurassic, like Jurassic Park, right? Um, And they've really broken down the Cenozoic because those are sort of the easiest to see in the rock record because they're the most recent and not much has been done to them in terms of erosion or things like that. And then you get way back here in the Silurian, Devonian, Ordovician, and Cambrian. This is when you had lots of, ocean critters and a lot of the fossils like trilobites that you see. In fact, around here in southeast Wisconsin, we have Silurian and Devonian age rocks mostly. So over by Miller Park, there's a cliff over there that's up against the VA cemetery. That is what's called a Silurian reef. So at one time, millions of years ago, it was a shallow, reef like the Great Barrier Reef in Australia, and all kinds of fossils in there. Now it's illegal to go dig in there, but that is a Silurian aged reef. Then you have the Permian here. At the end of the Permian is when a lot of things went extinct, including trilobites, and then you get into the Mesozoic. And then we all know at the end of the Mesozoic here, all the dinosaurs died out. So there's a lot of information on this particular chart. And again, if you look at the one on the left here, this short section here is the only part of that entire timeline that goes back to this is 4.5 billion years ago, and then this is 540 million years ago. So that's covering roughly 4 billion years. There was no life up until about 5.5 million years ago, or excuse me, 500 500 million years ago, excuse me. So there's a lot of information here, and this is what how really helps geologists understand what came first, what came second, sort of thing in the rock record. One of the downsides of the geologic timescale is that we can't always radiometric date everything and get really good actual numbers, because there are a lot of rocks that are not datable at all, especially sedimentary age rocks, because they don't contain the types of atoms that are required for it. That's the unfortunate reality. So they have to use relative dating, fossil records, and then correlation, like we mentioned, to match up all the different rock layers over large areas of large regions to do this. And it's been a lot of work, and it's been going on for hundreds of years now to get the geologic maps that you see, let's say of Wisconsin or whatever it is. A lot of work has gone into those. So there are a few ways of at least getting some type of numerical date for sedimentary strata, and that usually involves some type of igneous event. And what do I mean by that? So we have the volcanic ash bed here in green. The volcanic ash has the atoms needed to get a radiometric date. So it was dated at about 160 million years ago. All right. So that means that the Morrison Formation here has to be slightly older than 160 million years, and the Dakota Sandstone here has to be slightly younger than 160 million years. So that gives us a very narrow window of being able to determine when those particular geologic layers were formed. Now, the other way to do that is with the law of cross-cutting relationships, where you have this igneous dike cutting through all these particular layers. Okay, so that means A, the dike has to be younger than all the layers because it's cutting through them. And because it's igneous, again, it has the atoms that allow radiometric dating. They look at it, go, okay, this is 66 billion years old. And you could see it cuts through everything but the Wasatch. So that automatically means the Wasatch has to be younger than 66 million years. And that it means everything below that has to be older than 66 million years. And so that this is another way to determine sedimentary layers, is by using other relationships to figure it out. Okay, so this is chapter 11, geologic time, and it was a sort of a short chapter, but all of these laws and rules play a role in determining, allowing geologists to determine the succession of events in geologic time. And that over millions of years is no easy task. So over the last couple hundred years, humans have figured out ways to get them all to line up, so to speak, to where you have what we now call the geologic time scale. And obviously things are always changing a little bit in terms of, oh, this date could be changed by this much or that much. As the techniques in radiometric dating have gotten better, um, they've honed in on better and better dates, and they still find rocks that are older than the oldest known rocks by maybe a little bit, because again, those techniques. Some of the oldest rocks found on Earth, if you didn't know this, are up in Canada, what they call the Canadian Shield rocks. Those are usually anywhere from 4.2 to 4.5 billion years old. There's also those same age rocks, very, very old rocks in Australia. And every once in a while they say, oh, they found another oldest rock where they found a piece that might be 4.56 billion years or 4.57 billion years. So every once in a while you see that, and a part of that too is that, again, the radiometric dating techniques have gotten much better over time as well. There's a lot of interesting concepts, and when I've never been to the Grand Canyon, but I mean, it's just the perfect example to illustrate these geologic laws, horizontality and superposition and angular unconformities. All of these things, they're all there in the Grand Canyon. So if you either ever go there, or if you're looking at pictures of it, try to figure out, oh, hey, that's why this is there. That's why you have those angled rocks sitting on top of flat rocks, or excuse me, flat rocks sitting on top of angled rocks, because at one time they were also flat. They got uplifted, eroded, and now you got flat stuff on top of it again. And again, this goes back into how the theory of plate tectonics was formed. I think that chapter is coming up soon as well. How the theory of plate tectonics was formed, because you have to be able to match up not only what geologic the record says, but the timing. So if this wreck, if the, you know, like here in Wisconsin, for example, um, we don't have any Mesozoic rocks in Wisconsin. So during the Mesozoic, Wisconsin was in an erosional phase, not in a depositional phase, if that makes sense. I hope that makes sense. So in Wisconsin, all of the Mesozoic rocks have been eroded away from where we see. We have Paleozoic rocks here, although we have all the glacial stuff on top of it. Well, I hope you enjoyed this chapter and learned a little bit of something about it. It's been a while since I've had to talk about geologic time. It's kind of fun. And definitely, like I said, take a look at the Grand Canyon and just you just kind of marvel at it's like a living textbook for geology. It's used all the time because it is just so easy to understand these principles and laws in terms of how rock layers are formed. All right, we'll see you in the next chapter. Take care.